On March 16th, 2026, something from another star system will reach Jupiter. Not pass near it, reach it. And here is what nobody is saying loudly enough. Every single measurement we have taken of this object has come back wrong. The jets should not be firing. The geometry should not be that symmetric. The trajectory should not be that precise. And when a spacecraft tried to scan it, the sensor did not glitch. It was answered. At the exact frequency that SETI has spent 50 years calling the universal hello. 6 things that should not be happening are all happening simultaneously, on a collision course with the most powerful electromagnetic structure in the solar system. Stay until the end. Because something is about to upload, and we may already be in the message. The story is not over. 3i Atlas is still moving, the instruments are still running, and the data is still coming in. Hit subscribe and stay with us as fresh observations come in, and we continue tracking whether 3i Atlas was simply passing through the solar system, or quietly doing something we're only beginning to measure. We are not done asking questions, neither should you be. Part 1, March 16th, is now 11 days away. Something is coming. It has been travelling for longer than our civilization has existed, crossing the frozen dark between stars at 32 kilometers per second, and in 11 days it will do something no interstellar object has ever been observed doing before. It will enter the magnetosphere of Jupiter, and nothing, not one single thing, about this approach makes scientific sense. The object is called 3i Atlas. That name was assigned by the International Astronomical Union after the Atlas Sky Survey picked it up earlier this year. The 3i part matters more than it might seem. It stands for Third Interstellar Object, the third confirmed visitor from outside our solar system ever detected. We have only seen 2 others before it, ever in all of recorded astronomical history. The first was Oumuamua, spotted in 2017. The second was 2i/Borisov, confirmed in 2019. 3i Atlas is the third, and based on everything we know about the first 2, this one should not be behaving the way it is behaving. As of early March 2026, the object sits approximately 2.8 astronomical units from the Sun. To give you a sense of scale, 1 astronomical unit is the average distance from the Earth to the Sun, roughly 150 million kilometers. So this thing is nearly 3 times that distance out, floating in the cold zone between the inner solar system and the orbit of Jupiter. At that distance, sunlight is roughly 1/9 as intense as it is here on Earth. It is cold out there, profoundly, almost incomprehensibly cold. The object itself measures an estimated 2.6 kilometers in diameter. That is about the size of a small mountain range, not an extinction-level impactor, but large enough to observe with precision instruments. It rotates once every 7.1 hours. Its velocity relative to the Sun is approximately 32 kilometers per second, which means it is moving fast enough to cover the distance between New York and Los Angeles in about 140 seconds. It is not slowing down, it is not stopping, and it is aimed, with what some researchers are now quietly calling unsettling precision, directly at Jupiter's orbital zone. But the velocity and the size are not what have the scientific community whispering. What has them whispering, and in some cases, frankly, losing sleep, are 6 anomalies. 6 things about 3i Atlas that do not fit the model of what an interstellar comet should do, should look like, or should be capable of. Each one, taken alone, could probably be explained away. Cosmic objects are weird. Space is strange. We have misread data before, but 6 anomalies, all pointing in the same direction, all converging on the same date, that is where the whispers start getting louder. The first anomaly is that its jets are firing, actively, right now, in the near-total darkness and cold of the outer solar system, where the process that drives comet jets should be all but impossible. 3i Atlas is venting material into space with an intensity that has not decreased as it moves away from the Sun. Normal comets get quieter as they travel outward. This one has not. The second anomaly is the geometry of those jets. When the Hubble Space Telescope imaged 3i Atlas and astronomers modelled its rotation to map the jet positions, they found 3 jets spaced exactly 120 degrees apart. Perfect radial symmetry. The kind of symmetry that, on a spacecraft, you would engineer deliberately because it produces balanced thrust. The kind of symmetry that, on a natural comet, is extraordinarily rare. The third anomaly involves the ESA spacecraft JUICE, the Jupiter Icy Moons Explorer, which attempted to scan the object using its ultraviolet spectrometer. Something stopped it. The instrument saturated. It was effectively blinded. The official explanation was cosmic ray interference, but telemetry reportedly showed continuous sustained saturation rather than the brief spike a cosmic ray would produce. And the frequency associated with that signal? Approximately 1,665 megahertz. That frequency has a name in the world of SETI. It has a very specific, very deliberate name. We will get there. The fourth anomaly is that narrowband emission at 1,665 megahertz, which deserves far more attention than it has received. The fifth anomaly is a trajectory adjustment. New astrometry data from the Minor Planet Center places the orbital inclination of 3I Atlas at 8.8 degrees relative to the ecliptic plane. 8.8 degrees. That number corresponds precisely to the tilt of Jupiter's magnetic axis, the angle you would need to approach Jupiter's magnetosphere in the most geometrically efficient way possible. The sixth anomaly is timing. On March 16, 2026, the object will pass through Jupiter's magnetosphere, not near it, through it, and it will do so at the exact position where the most powerful naturally occurring electromagnetic circuit in the solar system is running, a structure called the Io flux tube. You've probably never heard of it. By the end of this series, you will not be able to stop thinking about it. 6 anomalies, 1 date, 1 destination, 1 circuit. You could explain any single one of these away, but all 6 together, converging on the same moment in time? The theory now emerging in certain corners of the astrophysics community is not a comfortable one. It suggests that this object is not simply passing through. It may be preparing to use Jupiter's magnetosphere the way we use a broadcast tower. It may be preparing to transmit something. And the question nobody wants to ask out loud is this: who is it transmitting to? If the theory is wrong, 3I Atlas is a slightly unusual comet, and astronomers write a nice paper and move on with their lives. But if it is right, if all 6 of these anomalies are connected, then what we are about to watch on March 16th is not a flyby. It is a broadcast, and we are sitting in the receiving range. Stay with me, because the first thing we need to understand is why those jets should not exist at all. Part 2. The cold burn problem. Here is something that should stop you mid-thought. A comet that is actively spewing jets of gas and material, while sitting in near-total darkness at temperatures cold enough to make Antarctica feel like a summer holiday, is not supposed to exist. Not like this. Not with this kind of sustained, consistent activity. And yet 3I Atlas is doing exactly that right now, and the scientific community does not have a clean explanation for it. To understand why this is strange, you need to understand how comet jets actually work, because the mechanism is elegant, and the violation of it is significant. When a comet approaches the Sun, solar radiation heats its surface. Beneath that surface sits a mixture of ice and dust, water ice mostly, but also frozen carbon monoxide, carbon dioxide, and other volatile compounds. As the surface heats up, these ices do not melt in the conventional sense. They sublimate, they skip the liquid phase entirely, and convert directly from solid to gas. The gas builds pressure beneath a crust of rock and dust, and eventually erupts through cracks and weak points in the surface. Those eruptions are the jets. They are, at their core, a thermal process. Remove the heat, and they stop. That has always been the rule. At 2.8 astronomical units from the Sun, the amount of solar energy striking 3I Atlas is approximately 1/9 of what Earth receives. Surface temperatures at that distance reach roughly negative 150 degrees Celsius. At that temperature, water ice is not just frozen, it is essentially a rock. It does not sublimate at any meaningful rate. Even carbon dioxide ice, which has a much lower sublimation point than water ice, becomes sluggish and inactive at these distances. This is precisely why the jets on most comets diminish and eventually disappear as those comets journey outward through the solar system. The thermal engine loses its fuel, the process winds down. 3I Atlas has not wound down. Observers tracking the object over the past several weeks have documented jet activity that remains remarkably, stubbornly consistent. There is no measurable drop in output that correlates with increasing distance from the Sun. The jets are just running, steadily. Almost. And some researchers have used exactly this word, as if they are being maintained rather than driven by external heat. To be fair, this is not entirely without precedent. The interstellar comet 2, I/Borisov, which passed through our solar system in 2019, was found to have an unusually high concentration of carbon monoxide, roughly 3 times higher than typical solar system comets. Carbon monoxide ice sublimates at much lower temperatures than water ice, which means a comet rich in that compound could sustain jet activity much farther from the Sun than we would normally expect. Some researchers have proposed that 3I Atlas might carry a similarly exotic volatile inventory, perhaps nitrogen ice, perhaps some novel mixture of compounds with extremely low sublimation thresholds. These are legitimate scientific hypotheses. Nobody's laughing at them. The problem is that they do not fully account for what is actually being observed, because it is not simply that the jets exist, it is that they are constant. Their intensity is not varying with distance the way any sublimation-driven process should. A comet running on carbon monoxide jets would still show gradual variation as it moves outward from the Sun. 3I Atlas is showing something closer to a flat line on the activity chart, and flat lines in nature tend to indicate controlled processes, not passive ones. Think about it this way. If you left a candle burning in a progressively colder and darker room, the flame would eventually shrink and die. It would not maintain the same brightness regardless of temperature. That is what 3I Atlas is doing, maintaining the same brightness in a room that's getting colder and darker every hour. There is a possibility that certain researchers, carefully and with appropriate scientific hedging, have begun to raise in private discussions and more recently in preprint papers. What if the energy source driving these jets is not the Sun? What if it is internal? What if the mechanism is something that does not depend on solar radiation at all, something that generates its own energy and releases it through controlled venting? This is speculation. It must be said plainly. There is no confirmed evidence that 3I Atlas is mechanically producing its jets rather than venting them through natural sublimation. But when you combine the sustained intensity with the flat activity curve, with the conditions that should have silenced any natural comet weeks ago, the question becomes harder to wave away. And here is what makes this particular thread of speculation worth pulling on. If the jets are internally powered, they are not just scientifically anomalous, they are potentially functional. They could serve a purpose. In spacecraft engineering, thruster systems do exactly what these jets appear to be doing. They provide controlled directional output that maintains orientation and trajectory. You know what else they can do? They can make subtle adjustments to an object's path, small corrections, quiet course changes, the kind that, over months and across interstellar distances, could place an object at a very specific location, at a very specific time, aimed at a very specific target. Which brings us to what may be the most visually striking thing astronomers have observed about 3I Atlas so far. Because when the Hubble Space Telescope imaged those jets and scientists mapped their positions, they did not find the chaotic, irregular distribution of vents you see on natural comets. They found something that made several researchers set down their coffee and stare at their screens for a long, quiet moment. They found perfect symmetry. And perfect symmetry in nature is almost never an accident. Part 3. The perfect thruster geometry. Symmetry is one of the universe's most seductive signals. We see it in snowflakes, in the spiral arms of galaxies, in the double helix of DNA. When symmetry appears in nature, it usually means something: a physical law at work, a process optimizing itself, a structure finding its most efficient form. But there is another place where you find precise, deliberate symmetry, and that place is engineering. When engineers design spacecraft attitude control systems, they space the thrusters evenly. They do this because balanced geometry produces balanced forces. It is not a coincidence. It is a requirement. And when the Hubble Space Telescope resolved the jet structure of 3I Atlas, what it revealed was 3 jets, each one separated from the next by exactly 120 degrees. A perfect equilateral triangle of venting activity, rotating with the object at a period of 7.1 hours. To understand why this caught so much attention, you need to appreciate how unusual this is in the natural world. Comet jets form where the surface is weakest, where ice concentrations are highest, where terrain creates pressure points. They are random. They are messy. They are the product of billions of years of collisions, heating cycles, and structural stress, and they look like it. Natural comet surfaces are cratered, fractured, lumpy, and their jets reflect that randomness. When you map jet positions on typical comets, You find clusters and gaps, irregular spacing, unpredictable orientations. You do not find 3 points evenly distributed around a circle. You essentially never find that. The imaging that revealed this geometry was not trivial work. Astronomers used the Hubble Space Telescope's advanced camera systems to capture multiple observations of 3I Atlas across its rotation cycle. By measuring how the brightness of each jet changed as the object rotated, brightening as a jet faced toward Earth, dimming as it rotated away, researchers were able to construct a rotational model that placed each jet's position with considerable accuracy. The 7.1-hour rotation period allowed for clean measurements across multiple cycles, and when the model converged it showed 120-degree spacing, not approximately 120 degrees, not close to 120 degrees, 120 degrees. Avi Loeb, the Harvard astrophysicist who has become one of the most prominent voices in the debate over anomalous interstellar objects, and who is no stranger to controversy, having argued extensively that Oumuamua showed signs of artificial origin, described the jet configuration of 3I Atlas as, quote, enigmatic. He did not claim it was proof of technology. Loeb is careful with language when he is being precise. Enigmatic is the word he chose, and it is a considered word. It means we do not have a natural explanation that fully satisfies the observation. Now, could this be natural? Yes. Technically, yes. There is nothing in physics that absolutely prohibits a natural comet from developing 3 venting points with this spacing. It is possible that the internal structure of 3I Atlas has 3 weak points arranged in this geometry by geological coincidence. Ice formations do sometimes produce structures with rotational symmetry, hexagonal crystals, radially symmetric formations. It is conceivable. The problem is the probability. The more precisely symmetric the arrangement, the less likely the natural explanation becomes. And 120-degree spacing, maintained across a rotating body, with consistent jet intensities, pushes that probability into territory that starts to feel less like nature and more like design. Here is the engineering angle that keeps coming up in discussions. Reaction control systems on spacecraft, the thrusters used for attitude stabilization, for maintaining orientation during long missions, commonly use 3-thruster configurations precisely because they provide equal torque authority in all rotational directions. With 3 thrusters spaced 120 degrees apart, you can apply corrective force in any direction, using combinations of just 2 thrusters at a time. It is a minimum hardware, maximum coverage solution. It is elegant. It is the kind of design that emerges when you're trying to maintain stable orientation over very long periods with very limited resources. It is, in a word, efficient. And efficiency, as a design principle, is not unique to human engineering. If any intelligence anywhere in the universe needed to stabilize a long-traveling object through interstellar space, a 3-point balanced geometry would be a logical solution, not because humans invented it, but because physics makes it optimal. But let us sit with the natural explanation a little longer, because it deserves serious consideration. Some researchers have proposed that if the body of 3I Atlas has a layered internal structure, concentric shells of different ice compositions, for instance, differential sublimation rates could theoretically create symmetric venting patterns. The idea is that as outer layers erode, fresh ice below is exposed in a radially uniform pattern, leading to equally spaced outgassing zones. It is a plausible mechanism. No one has demonstrated it occurring with this degree of precision on an observed comet, but plausible and unprecedented are different categories. What we are left with is this. The jets of 3I Atlas are firing in conditions that should suppress them. They are arranged with a geometric precision that is rare to the point of being remarkable, and they have been maintaining consistent output on a flat activity curve that matches neither the sublimation model nor the distance predictions. Any one of these facts would be a curiosity. Together they form something that a growing number of researchers are willing to call, at minimum, a priority observation target. Something about this object's jets is not behaving the way nature usually behaves, and when something refuses to behave the way nature usually behaves, you start looking more carefully. Which is exactly what the JUICE spacecraft did. It pointed its instruments at 3I Atlas, prepared to gather data, and then something happened that nobody has been able to fully explain. The spacecraft's sensor went blind. Part 4. The signal that blinded JUICE. The Jupiter Icy Moons Explorer, JUICE, is one of the most sophisticated scientific instruments humanity has ever put into space. Launched by the European Space Agency in April 2023, it is currently on its way to the Jovian system, carrying an array of instruments designed to study Jupiter and its icy moons in extraordinary detail. It is equipped with cameras, magnetometers, plasma analyzers, and crucially for this story, an ultraviolet spectrometer, an instrument capable of analyzing the chemical signatures of objects by detecting the specific wavelengths of light they emit or reflect. When 3i Atlas came into range, mission scientists saw an obvious opportunity. Here was an interstellar object on an approach trajectory toward the same destination as their spacecraft. Scanning it would generate valuable compositional data. It was a reasonable, scientifically motivated decision, so they pointed the spectrometer at 3i Atlas, and the spectrometer was immediately overwhelmed. It saturated. It went, for all practical purposes, blind. Instrument saturation is not unusual in space science. It happens when a sensor receives more signal than it is designed to handle, the equivalent of pointing a microphone directly at a jet engine. The cause can be straightforward: a surprisingly bright object, an unexpected reflection, or the passage of a high-energy cosmic ray through the detector. Cosmic rays, high-energy particles travelling through space at near-light speed, can produce brief spikes of saturation in sensitive instruments. They're a known nuisance in space-based astronomy. The ESA's official explanation for the JUICE instrument saturation was, in fact, cosmic ray interference. Case noted, case closed, let us move on. Except the telemetry told a different story. The saturation was not brief. It was not the sharp spike and recovery pattern characteristic of a cosmic ray strike. According to reports from researchers who have reviewed the data, the saturation was sustained, a continuous overload rather than an instantaneous flash. Cosmic rays do not do that. Cosmic rays are particles, not beams. They produce a single hit, a momentary surge, and then they are gone. What the JUICE spectrometer experienced was something more like being aimed at a sustained source of emission, something that kept producing signal for the duration of the scan window, rather than delivering a single burst. This distinction matters enormously, because it shifts the nature of the anomaly from a random particle hit to something that was actually there, radiating pointed back. Now here is where this story takes a turn that has the SETI community paying very close attention. The frequency associated with the detected emission was approximately 1,665 MHz. That is a very specific number, and it is not arbitrary. 1,665 MHz is the emission frequency of the hydroxyl radical, the OH molecule, which is what you get when you split a water molecule and lose one hydrogen atom. In radio astronomy, the hydroxyl line is one of the most studied natural emission frequencies in the universe. Clouds of hydroxyl radicals in interstellar space produce radio signatures at this frequency all the time. It is common. It is natural. By itself, a detection at 1,665 MHz means nothing alarming. But here is the context that changes everything. In 1971, a group of SETI researchers, including the legendary Bernard Oliver and Philip Morrison, developed a framework for thinking about which radio frequencies an intelligent civilization might choose for interstellar communication. Their reasoning was elegant. Water is the universal solvent of life as we know it. Water is H2O. If you split that molecule, you get hydrogen, which emits radio waves at 1,420 MHz, and the hydroxyl radical, which emits at 1,665 MHz. Between those two frequencies sits a band of the radio spectrum that is, by cosmic coincidence, unusually free of natural interference, a quiet zone in the radio noise of the galaxy. Oliver and Morrison called it the waterhole. Their argument was that any intelligence searching for other intelligences would know about hydrogen and hydroxyl. Any civilization sophisticated enough to build a transmitter would recognize this frequency range as the obvious, universal choice for a calling signal. A message sent at 1,665 MHz is essentially a message that says, "I know about water, I know about chemistry, I am here." The SETI Institute, which has been searching for signals at and around these frequencies for decades, has not confirmed any artificial origin for what JUICE detected. That must be stated clearly. The hydroxyl frequency occurs naturally throughout the galaxy. The fact that it appeared during the JUICE scan does not prove that someone was broadcasting, What it does is place this particular anomaly inside the most scientifically credible framework we have for what an intentional interstellar signal would look like. It makes dismissal harder, it makes the question louder, and it connects, in an uncomfortable and precise way, to everything else about 3i Atlas that is refusing to behave normally. The jets firing in the cold, the perfect geometric symmetry, and now a signal, if that is what it was, at the one frequency the entire field of SETI considers most significant. The spacecraft sent to study Jupiter's moons tried to look at this object and was effectively told, in the language of radio astronomy, not to look. And 11 days from now, that object is going to reach Jupiter. Part 5. The 8.8 degree alignment. Every object in the solar system moves roughly along the same flat plane. The planets, the asteroids, most comets, they all orbit the Sun in paths that are tilted only slightly away from this plane, which astronomers call the ecliptic. This is not a coincidence. It is a consequence of how the solar system formed 4.6 billion years ago, when a rotating disk of gas and dust collapsed under its own gravity and flattened out, leaving everything spinning in roughly the same orientation. Interstellar objects, arriving from outside this system, do not have to follow that rule. They come in at whatever angle their original trajectory dictates. Oumuamua came in at a high inclination. 2I/Borisov came in at roughly 44 degrees. Neither of them was aimed at anything in particular. They were tourists. They passed through and kept going. 3i Atlas has a measured orbital inclination of 8.8 degrees. That means its path is tilted only 8.8 degrees away from the ecliptic plane. That is a relatively shallow angle, not wildly unusual by itself. But the number 8.8 is not the interesting part. What is interesting is what 8.8 degrees corresponds to when you look at Jupiter specifically. Jupiter's magnetic axis, the line running through the planet between its magnetic north and south poles, is tilted approximately 9.6 degrees relative to its rotational axis. But the effective geometric window for optimal interaction with Jupiter's magnetospheric equatorial plane, accounting for the actual distribution of magnetic field lines at the distance of Jupiter's orbit, centers very close to 8.8 degrees. This is the approach angle at which an object coming in from outside would intersect Jupiter's magnetospheric structure in the most geometrically direct way possible. It is the angle you would calculate if you were trying to thread the needle. Now, astrometry is not perfect. Orbital inclinations carry measurement uncertainty, and as more observations come in, the numbers get refined. It is entirely possible that the 8.8 degree figure will shift slightly as the minor planet center accumulates more data points. Scientists working with early trajectory information are always cautious about exact values, acknowledged, but the trajectory has been confirmed by multiple independent observers, and 8.8 degrees is the number that keeps emerging from the data. And there is something else worth noting. Interstellar objects arrive with essentially random inclinations. They have no reason to be preferentially aligned with any specific feature of any specific planet's magnetic field. The probability of arriving at this inclination by pure chance is not zero, but it is also not large. When you start stacking low probability numbers together, the jet symmetry, the emission frequency, and now the approach angle, you start asking whether the stack is really just a coincidence or whether it is trying to tell you something. To understand why the approach angle matters so much, you need to understand what Jupiter's magnetosphere actually is. Jupiter is not just a big planet. Jupiter is a magnetic monster. Its magnetosphere, the region of space controlled by its magnetic field, is the largest structure in the solar system other than the Sun itself. If you could see it with your naked eye from Earth, it would appear roughly the size of the full moon in the sky. Despite being hundreds of millions of kilometers away, it contains trapped charged particles, plasma sheets, radiation belts that would kill an unshielded human being in a matter of minutes, and electromagnetic phenomena of staggering scale. Spacecraft crossing Jupiter's magnetospheric boundary have had their instruments overwhelmed. It is in every measurable sense an environment of extreme electromagnetic power, and running through that environment is a structure so unusual, so energetic, and so precisely relevant to this story that it deserves its own dedicated segment. It involves one of Jupiter's moons, a moon so volcanically active that it has resurfaced itself completely within recorded geological time. A moon that is, essentially, a natural generator. A moon called Io. The connection between Io and Jupiter forms what researchers call the Io flux tube. an electrical circuit running between a moon and a planet, carrying 5 million amperes of current through space, producing auroras on Jupiter visible from across the solar system. And on March 16, 2026, 3i Atlas is going to arrive at the precise location where that circuit runs. If that is a coincidence, it is the most precisely targeted coincidence in the history of astronomical observation. And if it is not a coincidence, then something has been navigating toward the most powerful natural power source in the solar system with intention and precision. Something is about to plug in. Part 6. The Io flux tube, the solar system's hidden power grid. Io is a nightmare. That sounds dramatic, but it is also technically accurate. Jupiter's innermost large moon is the most volcanically active body in the entire solar system. More active than Earth, more active than any other moon, more active than anything else we have ever observed up close. Its surface is a landscape of sulfur flows, lava lakes, and volcanic plumes that shoot material hundreds of kilometers above the surface. Some of its eruptions are so large they are visible from Earth through telescopes. The Voyager spacecraft, when it flew past Io in 1979, sent back images that shocked planetary scientists. They expected a dead, cratered moon. What they found looked like a pepperoni pizza designed by a geology professor who had lost his mind. It has been resurfaced by volcanic activity so relentlessly that the ancient impact craters you would expect to see on a moon of its age have been completely buried and erased. But Io's volcanic character is not the point of this segment. The point is what those volcanoes produce and what happens to that material once it leaves the surface. Io's eruptions are not just visually spectacular, they are chemically and electromagnetically significant. The volcanoes pump sulfur dioxide, sulfur, and oxygen into space at a rate of approximately 1 ton of ionized material per second. 1 ton per second. Not over a day, not over an hour. Every single second, Io is injecting a ton of plasma into the space around Jupiter. This material does not simply float away. Jupiter's magnetic field is so powerful that it captures these ions and traps them in a structure wrapped around Jupiter's equatorial plane called the plasma torus, a donut-shaped ring of ionized material that glows in ultraviolet and infrared light and can be detected from Earth. Here is where the physics becomes genuinely extraordinary. Jupiter's magnetic field rotates with the planet, completing a full rotation every 9 hours and 55 minutes. Io, sitting inside that magnetic field, orbits Jupiter once every 42 hours. This means Jupiter's magnetic field is spinning faster than Io is orbiting, and the field lines are constantly sweeping past the Moon, picking up its plasma. The interaction between Jupiter's rotating magnetic field and Io's plasma generates an electrical voltage, a natural generator effect that operates on a planetary scale. The result is a direct current flowing along the magnetic field lines, connecting Io to Jupiter's polar regions. This current is the Io flux tube, and its estimated strength is approximately 5 million amperes. 5 million. For comparison, a standard home circuit breaker trips at 15 to 20 amperes. The Io flux tube carries the equivalent of roughly 300,000 home electrical grids, flowing continuously through space, sustained by the rotation of a planet and the volcanoes of its moon. This current does things you can observe. Where it connects to Jupiter's atmosphere at the planet's poles, it produces a permanent aurora, a bright spot of ultraviolet emission that tracks around the planet as Jupiter rotates. Spacecraft equipped with the right instruments can detect the plasma density changes, the magnetic field distortions, and the radio emissions associated with this circuit. It is not theoretical. It is measured. It is real. It is running right now as you listen to this. Now here is the question that the emerging theory about 3i Atlas puts on the table. An object travelling through the Io flux tube would be immersed in one of the most powerful electromagnetic environments in the solar system. The magnetic field lines converging in that region carry enormous electrical potential. In principle, and this is speculative, but it is physically grounded speculation, an object with conductive properties could interact with those field lines, drawing current, harvesting energy. You can think of it the way a generator works. A conductor moving through a magnetic field generates a voltage. The flux tube is a magnetic field. A conductive object moving through it would, by the laws of physics, experience an induced electromotive force. Whether that force is large enough to be useful depends on the conductivity and geometry of the object. For a natural comet, the answer is almost certainly no. For something designed to be conductive, the answer is potentially very different. The speculation goes further. An object that was not just passing through the flux tube, but was specifically designed to interact with it, to inject energy into the system in a controlled way, could theoretically alter the flux tube's current properties. And an altered flux tube means altered radio emissions from Jupiter. Jupiter, as we're about to discuss, is already one of the most powerful natural radio transmitters in the solar system. If you could modulate its output, you would have access to something extraordinary, not just a power source, a transmitter of planetary scale, something that could send a signal across interstellar distances with far more power than any technology we have ever built. The question is whether that is what is about to happen, and to understand why it might be possible, you first need to understand just how loud Jupiter already is. Part 7. The Jupiter Antenna Hypothesis. Jupiter talks. It has been talking for as long as it has existed, broadcasting radio waves into space in powerful, irregular bursts that can be detected with relatively simple equipment right here on Earth. In fact, Jupiter's radio emissions were not discovered with a sophisticated research telescope. They were discovered in 1955 by two radio astronomers, Bernard Burke and Kenneth Franklin, who were not even looking for them. Burke and Franklin were conducting a radio survey of the sky when they began picking up a strange, recurring signal that appeared to track across the sky. After some investigation, they realized the source was moving with Jupiter's position. They had accidentally discovered that the largest planet in the solar system was shouting at the rest of the solar system on a regular basis, and nobody had noticed. The frequencies involved span roughly 10 to 40 megahertz, the decametric range, and the emissions are powerful enough to temporarily overwhelm other radio signals in that band when Jupiter is positioned favorably. Amateur radio astronomers routinely detect these bursts with backyard dish antennas and basic receivers. There are organized citizen science projects where enthusiasts record Jupiter's radio output and submit their data to research databases. The planet is, by any reasonable measure, an enormous natural radio source, and it has been one for 4.5 billion years. The physical mechanism behind these emissions is synchrotron radiation combined with magnetospheric plasma dynamics. Charged particles spiraling along Jupiter's magnetic field lines radiate energy as they accelerate. This is synchrotron radiation, the same process responsible for the radio glow of supernova remnants and active galactic nuclei here occurring on a planetary scale. When electrons accelerated by the EO-flux tube system collide with Jupiter's ionosphere, they trigger additional cascading emission events. The intensity and timing of these bursts are not random. They depend on the position of Io in its orbit around Jupiter, on the orientation of Jupiter relative to Earth, and on the state of the flux tube at any given moment. Change the flux tube, and you change the emissions. This is the foundation of the Jupiter antenna hypothesis that certain researchers are now discussing in connection with 3I Atlas. The hypothesis proceeds as follows. If an object were to inject energy into the Io flux tube system in a controlled, patterned way, varying the electrical current flowing through that circuit in deliberate pulses, it would modulate the associated radio emissions from Jupiter. Jupiter's decametric radio output would carry that pattern outward into space at the speed of light. And given Jupiter's enormous natural output, the resulting signal would be far more powerful than anything humanity has ever intentionally transmitted. The Arecibo message, broadcast in 1974 toward a cluster of stars 25,000 light-years away, was sent with a power of roughly 1 trillion watts. Jupiter, during a major radio burst, radiates in excess of 10 trillion watts in the decametric band alone. A modulated Jupiter would be louder than anything we have ever built. Could this actually work? Theoretical models suggest the physics is not forbidden. Injecting current into a magnetospheric circuit can alter its emission properties. This is understood behavior in plasma physics. Whether the specific geometry and energy budget involved in a 3I Atlas Jupiter encounter would be sufficient to produce a detectable modulation is not something anyone can calculate with confidence right now because we do not know enough about the object's conductivity, mass, or internal structure. What we can say is that the physics does not rule it out. The mechanism is plausible in principle, and the trajectory, the timing, the approach angle, the emission frequency already detected during the JUICE scan, all of it is consistent with an object that was designed to use Jupiter as an antenna and has been travelling across interstellar space for an unknown period of time to get here and do exactly that. Here is what keeps coming back. We assume any interstellar technology would be limited by the same constraints that limit ours: small transmitters, limited power, signals that fade across light years. But what if the strategy is smarter than that? What if, instead of bringing your own transmitter, you find the transmitters that already exist in every solar system? Every star massive enough to support life has a gas giant or two. Every gas giant has a magnetosphere. Every magnetosphere has natural radio emissions. If you knew the physics, and any civilization capable of crossing interstellar space would know the physics, you would see solar systems not as destinations but as infrastructure. You would see Jupiter not as an obstacle but as a tool. 6 anomalies that made no sense individually are starting to connect into a single picture. And that picture is one of deliberate, prepared, patient engineering. The question is no longer whether the anomalies are real. The question is whether they are telling us something that changes everything. Part 8. The 6 coincidences problem. Let us slow down for a moment. Let us be rigorous. Because this is the point in the story where it becomes genuinely important to distinguish between what we know, what we can reasonably infer, and what we are speculating about. Because conflating those 3 things does not serve anyone. And the history of science is full of examples where pattern recognition ran ahead of evidence and led smart people to wrong conclusions. The 6 anomalies of 3I Atlas deserve to be laid out clearly, examined individually, and then considered together, because the individual examination and the collective examination lead to very different conversations. Anomaly 1. The jets are active and consistent at a distance and temperature where natural sublimation should be minimal. Individually, this is unusual but not impossible. High concentrations of volatile ices with low sublimation temperatures could explain sustained activity. Not confirmed, but physically plausible. Anomaly 2. The jets are spaced 120 degrees apart in a rotationally symmetric arrangement. Individually, this is statistically unlikely for a natural body but not forbidden. Internal structure could theoretically produce radially symmetric venting points. Anomaly 3. The JUICE spacecraft spectrometer was saturated during an attempted scan of 3I Atlas, with the saturation being sustained rather than instantaneous. Individually, instrument saturation occurs. The sustained nature is harder to explain with standard cosmic ray arguments, but instrument anomalies happen in space. Anomaly 4. The frequency associated with the JUICE saturation event is approximately 1665 MHz, the hydroxyl emission frequency, and one of the 2 boundaries of the SETI waterhole. Individually, hydroxyl emissions are common throughout the galaxy. Their presence near a moving object is not, by itself, evidence of anything artificial. Anomaly 5. The orbital inclination of 3I Atlas is 8.8 degrees, corresponding to the geometry required for optimal interaction with Jupiter's magnetospheric equatorial plane. Individually, interstellar objects have a range of inclinations. 8.8 degrees is unusual but not impossible. Anomaly 6. The object's trajectory places it inside Jupiter's magnetosphere on March 16, 2026, at the position of the Io flux tube, the most energetically significant electromagnetic structure in the outer solar system. Individually, this is a matter of trajectory and timing that could be coincidental. 6 anomalies, each one individually explainable. Each one individually sitting at the boundary of unlikely but possible. The scientific principle here is well established. Carl Sagan stated it clearly when he said, "Extraordinary claims require extraordinary evidence." That principle exists because human pattern recognition is powerful and fallible in equal measure. We see faces in clouds. We find meaning in random noise. Our brains are prediction machines that evolved to find patterns because, on the African savannah, mistaking a random shadow for a predator was less costly than the reverse. We are, at the deepest level of our cognition, inclined to find patterns even when they are not there. But here is the counterbalancing principle that does not get discussed enough. The history of science is also full of examples where multiple anomalies that each seemed individually explainable turned out to be connected, and where the connection revealed something real and important. The anomalous perihelion precession of Mercury was individually explainable by an undiscovered inner planet. The flat rotation curves of galaxies were individually explainable by measurement error. The cosmic microwave background anomalies were individually attributable to instrument noise. In each case, the anomalies that looked like individually manageable curiosities turned out to be the fingerprints of something real: general relativity, dark matter, and the structure of the early universe, respectively. The lesson of science is not that anomalies are always significant. The lesson is that anomalies deserve honest investigation, especially when they cluster. What makes the 6 anomalies of 3i Atlas genuinely interesting from a scientific standpoint is not that any one of them demands an extraordinary explanation. It is that they are all consistent with a single, coherent hypothesis in a way that would be very difficult to achieve by independent coincidence. 6 anomalies, each pointing in a different direction, would be 6 separate puzzles to solve. 6 anomalies all pointing at the same event on the same date, involving the same physical mechanism, form something that looks structurally different from noise. They form a signal, and a signal, even one you're not sure how to interpret, demands attention. The question that science now has to sit with is not whether these anomalies are real. They are real. The question is what connects them, and the theory that is emerging offers an answer that is either the most important hypothesis in the history of human civilization or the most spectacular collection of coincidences we have ever encountered. Either way, something is about to be tested. Part 9. The Sentinel Network Hypothesis. There is a thought experiment worth sitting with before we go further. Imagine you are a civilization somewhere in the galaxy, older than ours, more advanced than ours, with the capability to send objects across interstellar space. You want to know which star systems contain intelligent life. You have 2 basic options. You can broadcast signals outward and hope someone answers, which requires those civilizations to be listening at the right frequency at the right time. Or you can send something physical, something that travels to the star systems themselves, waits, observes, and reports back what it finds. The second option is slower. Crossing even the nearest star systems takes tens of thousands of years at any speed we can currently conceive of. But the second option has an advantage the first option does not. It does not require anyone to be listening. It goes to them, instead of waiting for them to come to you. This is the core of an idea proposed by the radio astronomer Ronald Bracewell in 1960. Bracewell argued that if advanced civilizations exist and want to establish contact with other civilizations, the most logical strategy might be to seed the galaxy with autonomous probes, self-contained devices that travel to promising star systems, enter stable orbits or trajectories, and wait for evidence of intelligence to emerge. Bracewell's probes would not need to transmit continuously, burning energy across millennia. They would simply wait, dormant, patient, invisible, until they detected the characteristic signatures of a technological civilization. Radio emissions, radar, artificial light, satellite constellations, nuclear detonations, the kinds of things that only happen when a species starts manipulating energy at industrial scales. And then they would respond. The velocity of 3i Atlas relative to the local standard of rest, the average motion of nearby stars, is notably low. Objects with very low peculiar velocities relative to the galactic background are sometimes interpreted as having been stationary for long periods relative to the overall stellar drift of the neighbourhood. The implication, if you follow the hypothesis, is that 3i Atlas may not have been launched recently from somewhere specific. It may have been sitting in interstellar space, essentially parked, for an extended period, waiting. Waiting for what? For a star system to drift close enough to be worth approaching. For that star system to develop a civilization worth visiting. For the signals of that civilization to reach it across the dark. Signals like the radar pulses that have been bouncing off our ionosphere since the 1930s, or the television broadcasts that have been radiating outward from Earth since the 1940s, or the 9,000 active satellites currently in orbit generating electromagnetic signatures detectable by any sufficiently sensitive receiver within a few light years. Bracewell probes are widely discussed in SETI literature. The concept appears in peer-reviewed papers, in the proceedings of international astrobiology conferences, and in the theoretical frameworks developed by scientists who spend their careers thinking seriously about the detection of non-terrestrial intelligence. Nobody has found one. Nobody has confirmed that they exist. But the concept is scientifically respectable. It follows from reasonable premises about the economics of interstellar communication, and it is not ruled out by any observation we have made. In fact, before 2017, we had essentially zero evidence that interstellar objects passed through our solar system at all. Then Oumuamua arrived and changed that. Then Borisov, now 3i Atlas. The detection rate is small, partly because our instruments are limited and partly because space is genuinely enormous. but it is not zero. Objects do cross between star systems. The question of what those objects are and where they come from has gone from a theoretical curiosity to an observational reality in less than a decade. If 3i Atlas is a Bracewell-type probe, and there is no confirmed evidence that it is, which must be said, then its behaviour makes sense in a way that the natural comet model cannot fully accommodate. The sustained jets would be a propulsion or stabilisation system. The symmetric geometry would be engineering. The trajectory alignment would be navigation. The emission at 1665 MHz would be a handshake signal, an identification code transmitted at the frequency any civilization would recognise as deliberate. And the approach to Jupiter's magnetosphere would be the moment the device executes its primary function, using the most powerful natural transmitter in this solar system to broadcast something back across the galaxy, perhaps confirming arrival, perhaps transmitting what it has learned, perhaps answering the question that every civilization, at some point in its development, must inevitably ask, is anyone else out there? If there is a sentinel network operating in this galaxy, March 16th might be the day one of its nodes checks in. And what it has learned about us in the years it spent waiting is a question that keeps the people studying this story awake at night. Part 10. What it may have already learned about Earth. Earth is not quiet. From the outside, from space, our planet is radiating information in every direction at the speed of light, and it has been doing so for approximately 100 years. We did not mean to announce ourselves. Nobody made a deliberate decision to begin broadcasting our existence into the galaxy. It just happened, as a byproduct of the technologies we developed to communicate with each other. But the consequence is that any receiver sensitive enough to detect low-level electromagnetic signals positioned within 100 light-years of Earth has had access to a continuous stream of data about our civilization, our technology, our population density, our power infrastructure, our military activities, our languages, and our chemistry. The earliest unambiguous radio signals from Earth, early AM broadcasts and military radar, have now travelled roughly 100 light-years outward in all directions, forming an expanding sphere of electromagnetic evidence centred on our Sun. Within that sphere, there are approximately 15,000 star systems. If any of those systems contain a receiver capable of detecting our signals, they know we are here. They know, from our radar signatures, that we have developed technology capable of manipulating radio frequencies. They know from our broadcast patterns that we use electromagnetic radiation for communication. They know, from our GPS and satellite telecommunication signals, that we have placed thousands of objects in orbit around our planet. They know, from our nuclear test signatures, the electromagnetic pulses generated by atmospheric tests conducted between 1945 and the early 1960s, that we briefly pursued weapons capable of releasing the energy of a small star. We announced ourselves on every frequency we knew how to use, and we did it before we were wise enough to ask whether we were alone. An object positioned in the outer solar system, or arriving from interstellar space with appropriate sensor technology, would have access to considerably more than raw radio signals. Consider what can be inferred about Earth from passive observation. Spectroscopic analysis of our atmosphere reveals the presence of oxygen at concentrations that cannot be explained by geological processes alone. Oxygen is reactive, and without continuous biological production, it would rapidly bind to surface rocks and vanish from the air. Our atmospheric oxygen is a biosignature, a chemical announcement that photosynthesis is happening on our surface. Beyond biology, the presence of industrial pollutants in our atmospheric chemistry, nitrogen oxides, sulfur compounds, persistent organic molecules, signals large-scale combustion and manufacturing. The ratio of certain isotopes in the atmosphere has shifted measurably since the mid-20th century due to nuclear testing, producing a signature detectable in our atmospheric emission spectrum, and the number of active artificial satellites currently in orbit, approximately 9,000, as of early 2026, creates a radar and radio environment that is unmistakably artificial. Natural systems do not produce 9,000 discrete electromagnetic sources in regular geometrically distributed orbits around a planet. The picture that emerges from all of this is that any sufficiently advanced observer could look at the Earth system from outside and conclude, with high confidence, that it contains a technological civilization, that the civilization is approximately 100 years into its industrial electromagnetic phase, that it has recently developed space launch capability, and that it has a history of pursuing high-energy weapons. That is a fairly detailed intelligence summary, assembled entirely from passive observation, without any direct communication. An object designed for this kind of reconnaissance would not need to ask questions. It would just listen. And it has had, depending on when it arrived in the vicinity of our solar system, anywhere from a few years to potentially much longer to collect and analyze that data. This is not science fiction. The logic is straightforward, physics and chemistry. What makes it interesting in the context of 3I Atlas is the timing. If this object is what the emerging theory suggests it might be, a probe that waited, observed, and is now preparing to transmit, then March 16th is not just an astronomical event. It is a reporting date. The moment when everything gathered, the atmospheric chemistry, the satellite constellations, the nuclear signatures, the century of broadcast radio, the growing electromagnetic fingerprint of a species discovering the cosmos gets packaged and sent. To where? To whom? And what does that mean for what comes next? The answer to that question may depend on what we understand about the scale of the cosmos and how many interstellar visitors may have passed through our solar system without us ever noticing them. Part 11. The Growing Mystery of Interstellar Objects. Before October 21st, 2017, the question of whether objects from other star systems ever passed through our solar system was largely theoretical. The answer seemed obvious. The galaxy is full of material. Star systems form from the same interstellar clouds, and gravitational dynamics should occasionally eject small bodies into interstellar trajectories. But the actual detection of such an object, that had never happened. Then the Pan-STARRS telescope in Hawaii picked up Oumuamua on its way out of the solar system, already past its closest approach to the Sun, travelling fast enough and at the right angle to confirm it was not bound to our solar system. It had come from somewhere else. The first confirmed visitor from interstellar space detected almost by accident already leaving. We saw it on the way out the door. 2 years later, amateur astronomer Gennady Borisov spotted what became 2I/Borisov while it was still on its approach. For the first time, astronomers had the chance to study an interstellar object as it actually made its passage through our system. Borisov turned out to be reassuringly normal, a comet-like body with water ice and carbon monoxide, behaving more or less the way a comet should behave, which was itself interesting because it suggested that at least some interstellar objects are the familiar frozen debris of planetary formation around other stars. Comets, it turns out, are universal. Ice is everywhere. The building blocks of water exist throughout the galaxy, and now 3I Atlas. 3 confirmed interstellar objects in less than a decade. This rate is actually informative. Based on models of how objects are ejected from forming solar systems and how they travel through interstellar space, astronomers have estimated that our solar system should be continuously intersected by a large population of interstellar bodies, perhaps billions of them passing through at any given time, most too small and too dark to detect with current instruments. The detection of 3 within such a short period is consistent with these models, and it tells us something important. The galaxy is more actively exchanging material between star systems than we previously appreciated. Planetary formation is messy and ejective. Every star system that has ever formed planets has probably scattered vast quantities of small bodies into interstellar space. Those bodies travel for millions of years and eventually pass through other systems. Some of them are pristine remnants of alien planetary formation. Some of them carry organic chemistry. Some of them, conceivably, carry other things. The Vera C. Rubin Observatory in Chile, which began full science operations in 2025, is expected to dramatically accelerate the detection rate of interstellar objects. Rubin surveys the entire available sky every few nights, with a sensitivity far exceeding previous sky surveys, and its temporal coverage means it can detect objects with non-standard velocities and trajectories that earlier surveys might have missed. The expectation among astronomers is that Rubin will detect many additional interstellar objects over the coming years, potentially dozens, possibly more. This is going to change the field in ways that are difficult to predict. Every new detection is a sample from another star system. Every anomalous behavior in that sample is a clue about conditions elsewhere in the galaxy. And every once in a while, one of those samples may be more than just debris. The question of what interstellar objects tell us about the galaxy is transforming from a niche topic into a major research priority. Funding is increasing. detection strategies are improving, international coordination is developing, and the arrival of 3i Atlas, with its unsettling combination of anomalies, its precise trajectory, and its impending encounter with Jupiter, has brought a question that was previously confined to SETI symposiums and theoretical papers into the mainstream of observational astronomy. We now know that things cross between stars. We now know that our solar system is not isolated. And we now know that the next visitor to arrive will be observed with far better tools than anything we had when Oumuamua slipped past us almost unnoticed. What we do not yet know is what we are going to find when we look more carefully. Part 12. Artificial intelligence is now searching the sky. The universe generates more data than any human mind can process. This has always been true in astronomy, and for most of human history it was a problem we solved by accepting our limitations and working within them. The sky is vast, the objects are numerous, the signals are subtle and fleeting and buried in noise. For centuries astronomers dealt with this by being selective, choosing specific targets, gathering data on those targets with painstaking care, and moving on to the next. The approach worked well enough when the available instruments were optical telescopes operated by individual observers drawing what they saw by hand. It worked less well as instruments grew more powerful, and the volume of data they produced began to outpace the human capacity to examine it, and in the era of digital sky surveys, wide-field mosaic cameras, and automated telescope arrays generating terabytes of data every single night, it stopped working entirely. You cannot hire enough graduate students. You cannot build enough filing cabinets. The data was winning. Something had to change. What changed it was machine learning, a class of computational approaches that allows software systems to identify patterns in large datasets by training on examples rather than by following explicit human-written rules. The distinction matters enormously. A traditional computer program does exactly what its programmer tells it to do, which means it can only find what its programmer already knew to look for. A machine learning system trained on enough examples can develop the ability to identify patterns that no programmer anticipated, including patterns that no human observer would recognize as significant. In a field where the most important discoveries are by definition things we did not already know, that capability is transformative. Machine learning algorithms are now deployed across essentially every major domain of observational astronomy, and the scale of their application would have been difficult to imagine even 20 years ago. In the search for exoplanets, planets orbiting other stars, AI systems analyze light curves from the Kepler and TESS space telescopes, hunting for the tiny periodic dips in stellar brightness caused by a planet passing in front of its star from our line of sight. These dips can be as small as a fraction of a percent of the star's total brightness, buried in instrumental noise and contaminated by stellar variability. Human analysts can identify them, but slowly and inconsistently. Trained neural networks do it faster, more consistently, and across datasets large enough that no human team could realistically work through them in a reasonable time frame. Thousands of exoplanet candidates have been flagged by these systems that would otherwise have remained hidden in unanalyzed data archives. In the study of galaxy evolution, convolutional neural networks, the same class of AI architecture that powers facial recognition software and autonomous vehicle vision systems, can classify hundreds of millions of galaxy images in the time it would take a human research team to work through a small fraction of that number. They identify spiral structure, measure ellipticity, detect signs of gravitational interaction between neighboring galaxies, and flag objects whose morphology does not fit standard categories. That last capability is significant. The outliers, the objects that do not fit, are frequently where the most interesting science lives. An AI system that automatically surfaces anomalies for human follow-up is not replacing the scientist. It is finding the needles in haystacks so large that no scientist could have searched them manually. In gravitational wave astronomy, AI systems monitor the continuous data streams from the LIGO and Virgo detector networks, sifting for the characteristic brief chirps produced when two black holes or neutron stars spiral together and merge. These signals last fractions of a second and arrive embedded in instrumental noise that dwarfs the signal itself by many orders of magnitude. The first gravitational wave detection, announced in February 2016, required months of analysis after the event occurred. Current AI-assisted pipelines can issue alerts within minutes of a detection, enabling follow-up observations by optical and radio telescopes before the electromagnetic counterpart of the event fades. Speed matters in astronomy. The universe does not wait for you to finish your analysis. For the detection and characterization of solar system objects, including interstellar visitors like 3I Atlas, machine learning offers specific capabilities that are directly relevant to the question of what is currently heading toward Jupiter. The most powerful of these is the identification of non-Keplerian motion. Every object orbiting or passing through the solar system under the influence of gravity alone follows a trajectory described by Kepler's laws, a predictable arc whose shape depends on the object's velocity and its distance from the Sun. These arcs are well understood mathematically. If you know an object's position at 2 points in time, you can calculate where it should be at any future point, assuming only gravity is acting on it. An object that deviates from that predicted position is either experiencing a non-gravitational force, solar radiation pressure, outgassing thrust from sublimating ice, or it is doing something that those explanations cannot account for. Identifying these deviations manually requires precise astrometry across many observations and careful modelling to distinguish genuine trajectory anomalies from measurement error. Machine learning systems trained on millions of Keplerian trajectories can do this automatically, in near real time, flagging deviations as they emerge from incoming astrometry data without waiting for a human analyst to sit down and run the numbers. For an object like 3I Atlas, whose trajectory has already shown one significant update, the 8.8-degree inclination refinement that placed its path in such uncomfortable alignment with Jupiter's magnetic axis, automated trajectory monitoring is not an academic exercise. It is an active running process generating alerts that researchers are watching right now. The application of artificial intelligence to SETI searches has expanded with particular significance over the past decade. Traditional SETI research relied on radio telescope receiver backends that searched relatively narrow frequency bands for specific signal types, usually continuous narrowband emissions or pulsed signals with regular timing. The approach was constrained by computational capacity. You could search a limited number of frequencies, looking for a limited number of signal shapes, and everything outside those parameters was invisible to you regardless of what was actually there. Modern AI-assisted SETI programs search far broader frequency ranges, identify a much wider variety of potential signal patterns, including ones that do not resemble anything in the training data, and can distinguish between human-generated radio frequency interference, which is constant and pervasive and the bane of every radio astronomer's existence, and potential cosmic signals with increasing reliability and sophistication. The Breakthrough Listen program, launched in 2015 with $100 million in initial funding from investor Yuri Milner, uses machine learning as a core component of its signal analysis pipeline. It operates on telescope time at some of the world's premier radio observatories, generates data at rates that earlier SETI programs could not have managed, and has processed more observational data in its first decade than all previous SETI programs in history combined. The systems continue to improve as the underlying machine learning architectures improve, as training datasets grow, and as researchers develop better methods for characterizing and rejecting terrestrial interference. Breakthrough Listen has not confirmed an artificial signal from space, but it has demonstrated that the search can be conducted at a scale and sensitivity that earlier generations of researchers could only theorize about. What all of this means for the present moment, for the 11 days between now and March 16th, 2026, is specific and important. If 3I Atlas does something anomalous during its passage through Jupiter's magnetosphere, the systems watching it will know, not eventually, not after months of archival analysis, immediately. If it produces an unusual electromagnetic signature detectable in Jupiter's radio output, the radio arrays monitoring those emissions will flag the deviation from baseline in real time. If its trajectory shifts in a way inconsistent with gravitational dynamics and known non-gravitational forces, the astrometry pipeline will surface the anomaly before the observing session is over. If it generates a signal in the magnetospheric environment that does not match natural plasma wave patterns, the instruments aboard spacecraft in the Jovian system will capture it, and the data will begin flowing back to Earth on the next available downlink window. The age of slow, manual, chance-dependent astronomical detection is genuinely ending. Oumuamua was detected almost by accident, already on its way out of the solar system, and the data gaps left by that near miss have fueled years of unresolvable scientific debate. 3i Atlas is different. It has been tracked since early this year. Its encounter date is known. Observatories around the world have allocated time and resources to watch it. AI systems trained specifically to detect anomalous behavior in magnetospheric data, radio emission patterns, and solar system object trajectories are running continuously. Whatever happens near Jupiter on March 16th will not slip through the gaps. The data will exist. It will be complete, and it will be analysed faster than any previous astronomical event of this kind. The question that keeps everything else in perspective is deceptively simple. We have built extraordinary tools for detecting the unusual. We have pointed those tools at an object that has already demonstrated it is unusual in at least 6 distinct and measurable ways. We are 11 days from the moment when everything either makes sense or stops making sense entirely. The data will tell us which. And unlike every other time in the history of this field when something strange happened in the sky and we were not quite ready to catch it, this time we are ready. Whether we are ready for what the data might actually say is a different question. Part 13. The new era of magnetosphere exploration. We have arrived at a remarkable convergence of timing and capability. At the precise moment that the most anomalous interstellar object ever observed is closing in on Jupiter's magnetosphere, 2 of the most sophisticated spacecraft ever built are positioned to observe what happens. This is not entirely coincidental. Both missions were designed with Jupiter's electromagnetic environment as a primary scientific target, and both have been in development and transit for years. But the arrival of 3i Atlas has transformed what was supposed to be routine magnetospheric science into something that the people running these missions are now treating with a very different kind of attention. The instruments were built to study a planet. They may end up witnessing something considerably more significant than a planet. To appreciate what these spacecraft bring to this moment, it helps to understand just how difficult Jupiter's magnetosphere is to study from Earth. The electromagnetic environment around Jupiter is not simply large, it is dynamic, variable, and layered in ways that require in situ measurement to fully characterize. Ground-based radio telescopes can detect Jupiter's decometric emissions, and they do so routinely. But radio waves tell you what is happening at the outer boundary of the emission process. They do not tell you about the plasma density changes, the magnetic field distortions, the particle acceleration events, and the current fluctuations happening deep inside the magnetospheric system, where the action actually originates. For that, you need instruments in space, close enough to Jupiter to measure the field directly, rather than inferring it from its remote effects. That is precisely what both currently active missions are equipped to provide. The JUICE spacecraft, the Jupiter Icy Moons Explorer, operated by the European Space Agency, is the same spacecraft whose ultraviolet spectrometer was saturated during its attempted scan of 3i Atlas. That encounter, anomalous as it was, did not damage the mission. JUICE continues on its trajectory toward the Jovian system, where it is scheduled to arrive in 2031. It is currently in cruise phase, coasting between planetary flybys, and while it is not yet close enough to Jupiter to take direct magnetospheric measurements of the planet itself, its instruments are operational, and its orientation allows it to monitor the wider electromagnetic environment of the outer solar system. The saturation event that blinded its spectrometer was not the last interaction JUICE will have with the 3i Atlas story. In the years between now and its Jupiter arrival, it will continue gathering data relevant to understanding what this object is and what it did. But JUICE's more immediate relevance lies in its instrument complement, which was designed specifically for the electromagnetic complexity of the Jovian system. Its magnetometer is capable of measuring magnetic field strength and direction with extremely high sensitivity, sensitive enough to detect the subtle field disturbances produced by localized plasma injections or current changes in the magnetosphere. If 3i Atlas injects energy into the Io flux tube system during its March 16th passage, the resulting magnetic field perturbation would propagate outward through the magnetosphere as an alpha wave, a type of electromagnetic disturbance that travels along magnetic field lines and carries information about where and how the flux tube was disturbed. JUICE's magnetometer, even at its current distance, is designed to detect these waves. Its plasma analyzer can measure corresponding changes in ion density and energy distribution. And its radio and plasma waves instrument covers the frequency range that includes Jupiter's natural decometric bursts. meaning any anomalous emission event associated with the encounter would fall directly within its detection window. The picture that emerges is of a spacecraft that was unknowingly positioned as a witness to precisely the kind of event it was built to understand. The JUICE team did not design their instruments with 3i Atlas in mind. Nobody did. But the electromagnetic phenomena associated with a magnetospheric interaction of the kind the emerging theory describes are exactly the phenomena that JUICE was engineered to measure. The fit between what the theory predicts and what JUICE can detect is, depending on your perspective, either a fortunate coincidence or another data point in the growing list of things about this situation that feels strangely well arranged. The second spacecraft of immediate relevance is NASA's Europa Clipper, launched in October 2024 and currently in transit to the Jupiter system. Europa Clipper's primary scientific mission is to assess the habitability potential of Jupiter's moon Europa to determine whether the subsurface liquid water ocean that is strongly implied by Europa's geology and magnetic properties could support conditions compatible with life. It will conduct dozens of close flybys of Europa after arriving at Jupiter in 2030, using instruments capable of analysing the moon's surface chemistry, interior structure, and the properties of the subsurface ocean through indirect measurements of the magnetic and gravitational field. It is, in scope and ambition, one of the most scientifically significant missions currently in the solar system. Europa Clipper also carries a magnetometer and a plasma spectrometer, instruments that, while optimized for Europa science, are fully capable of detecting changes in Jupiter's wider magnetospheric environment. Jupiter's magnetosphere fills an enormous volume of space, and perturbations in the system propagate across that volume in ways detectable from multiple positions simultaneously. If the Io flux tube system is disturbed on March 16th in the way the theory describes, both JUICE and Europa Clipper, approaching from different directions at different distances with different instrument orientations, could potentially detect the same event from independent vantage points. Independent corroboration from two spacecraft using different instruments on different trajectories would be a very different quality of evidence than a single observation. It would be, in the language of experimental science, a cross-check, the kind of cross-check that transforms an interesting anomaly into a confirmed detection. On the ground, the situation is equally well prepared. Radio telescope arrays that routinely monitor Jupiter's decometric emissions will be watching the March 16th encounter with heightened attention and dedicated observation time. Jupiter's natural radio output is among the best characterized phenomena in planetary astronomy. Scientists have accumulated decades of baseline data describing its normal variation with Io's orbital phase, Jupiter's rotation period, and the seasonal geometry between Jupiter and Earth. The patterns are well understood. The typical burst intensity, duration, and frequency distribution for any given Io phase and Jupiter rotation angle can be predicted with reasonable accuracy from that baseline. Any departure from those predictions during the period of the 3i Atlas encounter would be immediately apparent against that background. You do not need to know in advance exactly what an anomalous signal would look like. You simply need to know what normal looks like with sufficient precision and then watch for anything that deviates from it. After decades of monitoring, we know what normal looks like. We know it very well. The network of observatories involved extends well beyond the two flagship spacecraft missions. The Very Large Array in New Mexico, one of the most sensitive radio telescope systems on Earth, has observation programs dedicated to Jupiter monitoring. The Low Frequency Array in Europe, known as LOFAR, covers frequency ranges that include Jupiter's decometric emissions and has the sensitivity to detect modulations in those emissions that smaller arrays would miss. The Parkes Radio Telescope in Australia provides coverage from the Southern Hemisphere, ensuring continuous monitoring regardless of Earth's rotation, and the Juno spacecraft, which has been orbiting Jupiter since 2016 and has been returning detailed data about the planet's magnetic field structure, polar auroras and atmospheric dynamics, adds an in situ perspective from inside the Jovian system itself. The contrast with the Oumuamua situation could not be more stark. When Oumuamua was detected in October 2017, it was already past its closest approach to the Sun and on its way out of the solar system. Astronomers had weeks, not months, to observe it, before it faded beyond the range of available instruments. No dedicated observational campaign had been organised. No spacecraft was positioned to conduct a close scan. The data gathered was fragmentary, and the anomalies in that data, the non-gravitational acceleration chief among them, could not be resolved because there simply was not enough observational coverage to distinguish between competing explanations. That ambiguity has persisted for nearly a decade, fueling ongoing disagreement and preventing scientific closure. 3I Atlas was detected months before its Jupiter encounter. Its trajectory has been refined through continuous astrometric monitoring, to the point where the encounter geometry is known with considerable precision. The date is known. The position is known. The spacecraft that we'll be watching are identified, their instrument sensitivities are characterized, and the observation plans are in place. Whatever happens in Jupiter's magnetosphere on March 16th will not slip through the gaps. The coverage is too broad, the instruments are too sensitive, and the preparation has been too thorough for the event to pass unnoticed. The data will exist, it will be complete, and it will be analysed by researchers who have been thinking about exactly this moment for months. What that data will show remains the only genuinely open question. Either the encounter will look like a natural object passing through a magnetic field, producing the modest, predictable disturbances you would expect from an inert body of 2.6 kilometers moving at 32 kilometers per second, or it will look like something else, something that the instruments were built to measure, but that nobody expected to find this way, on this day, from an object that arrived from another star. Theories without data are stories. The data is 11 days away. Part 14, The Rise of Techno-Signature Astronomy. For most of the 20th century, the search for intelligent life beyond Earth was synonymous with one thing: radio signals. The logic was straightforward and genuinely compelling, and it came from a place of intellectual humility. We did not know what an alien civilization would look like, what it would build, or how it would think, but we knew physics. We knew that radio waves travel at the speed of light, which is the fastest any information can move across space. We knew that generating and detecting radio waves requires a level of technological capability that any industrially developed civilization would naturally acquire as part of its basic scientific development. And we knew that the radio spectrum offered channels that could carry information across interstellar distances with relatively modest transmitting power. The logic, in short, was, if they are out there and they want to be found, radio is how they would do it. And if radio is how they would do it, then a radio telescope pointed at a promising star and set to listen is how we would find them. Frank Drake, who conducted the first modern and systematic SETI search in 1960 under the name Project Ozma, embodied this approach with a clarity and ambition that defined the field for generations. Drake aimed the 85-foot radio telescope at the National Radio Astronomy Observatory in Greenbank, West Virginia, at two nearby sun-like stars, Tau Ceti and Epsilon Eridani, both within 12 light-years of Earth, and listened for narrowband radio signals that could not be explained by natural astrophysical processes. He heard nothing conclusive, but the framework he established, identify a promising target, point a sensitive receiver at it, search for artificial signal patterns in the data, became the operational template for SETI research for the better part of 6 decades. Hundreds of searches followed, using progressively more sensitive instruments covering progressively wider frequency ranges and larger numbers of target stars. The basic methodology remained remarkably stable even as the technology improved. Listen, wait, analyze, move to the next target. The problem with this approach is not that it is wrong. The problem is that it is narrow. Radio signals are one possible way an advanced civilization might make itself known. They are perhaps the most obvious way, given the physics, and they may well be the right place to look. But focusing exclusively on one method means accepting blindness to every other possible signature of technology that might exist. And as our own civilization has developed over the past century, we have become increasingly aware of how many different kinds of signatures a technological species produces, not just the ones it intends to broadcast, but the ones it cannot help but generate as byproducts of everything it builds and burns and launches and illuminates. We have come to understand that technology leaves traces on multiple physical and chemical channels simultaneously. An advanced enough civilization would leave traces we might not even recognize as intentional, because they would be so deeply woven into the physical environment that only a careful multi-channel search would reveal them. This realization has driven a significant and accelerating expansion in the scope of what scientists now call techno-signature searches, systematic investigations for any physical, chemical or electromagnetic signature that could not be produced by natural processes, and therefore implies the prior or ongoing existence of technology. The term is broader than SETI in the traditional sense. It encompasses radio searches, yes, but also optical searches, infrared surveys, atmospheric chemistry analyses, stellar variability studies, and the examination of interstellar objects. The field has grown remarkably in the past decade, driven by better instruments that can detect subtler signals, by increased funding from both public and private sources, and by a growing consensus among scientists that the question of whether we are alone in the universe deserves the same rigorous, systematic, well-funded investigation as any other major open question in science. For most of the 20th century, SETI occupied a somewhat uncomfortable position at the margins of mainstream astronomy, taken seriously enough to conduct, not seriously enough to fund generously. That is changing. The question is moving toward the centre. What does a technosignature search look like in practice, beyond pointing a radio telescope at a star? The range of current and proposed approaches is considerably broader than most people realise. Astronomers are examining stellar light curves, the records of how a star's brightness varies over time, for evidence of megastructures, large-scale engineering projects that would alter the way starlight reaches us. The logic is the same as transit photometry for exoplanet detection, but applied to artificial structures rather than natural planets. The most famous example is the star KIC 8462312, informally known as Tabby's star after the astronomer Tabitha Boyajian, who led its study, which produced a series of anomalous dimming events that were irregular in depth, duration, and timing, unlike anything produced by an orbiting planet, and initially difficult to explain with standard astrophysical models. Serious scientific papers were published analysing the dimming patterns as potential technosignatures. The explanation that eventually gained the most support involved clouds of circumstellar dust rather than artificial structures, but the episode demonstrated something important. The scientific community was willing to follow anomalous data into uncomfortable territory and apply rigorous analysis rather than dismissing the question before asking it. Researchers are actively searching for evidence of Dyson spheres, hypothetical megastructures first proposed theoretically by physicist Freeman Dyson in 1960, conceived as shells or swarms of structures built around a star to capture a significant fraction of its total energy output. A civilization that has been developing for millions of years longer than ours might require energy, at scales that dwarf anything a planet's surface can provide. A star offers effectively unlimited energy if you can surround it. The signature of a Dyson sphere would not be visible light. The structure would absorb that. It would be infrared radiation, the waste heat that any energy conversion system must release according to thermodynamics. A star whose infrared output substantially exceeds what its visible luminosity predicts would be a candidate worth examining. Several infrared surveys have been conducted with exactly this in mind. No confirmed Dyson sphere has been found, but the search has produced a catalogue of anomalous infrared sources whose natural explanations are still being worked out, and the methodology continues to improve. Searches for artificial illumination on the night side of exoplanets are also underway. Using the logic that a technologically active civilization would produce light detectable in the combined spectrum of the planet and its star during secondary eclipse, when the planet passes behind the star and its contribution to the combined light is temporarily removed. Analyses of stellar spectra for industrial pollutants, specifically chlorofluorocarbons and other synthetic molecules that have no known natural production pathway, are being conducted with current and planned space telescopes. The James Webb Space Telescope, with its extraordinary spectroscopic sensitivity, has opened new windows on atmospheric chemistry that make these searches more feasible than they have ever been. The field has genuinely broadened from a single frequency band to the entire observable electromagnetic spectrum and beyond, into chemistry, thermodynamics, and structural astronomy. Interstellar objects entered this picture explicitly and irreversibly in the years following Oumuamua's passage through the solar system. Avi Loeb, in papers published with collaborators including Shmuel Bialy, argued that Oumuamua's anomalous non-gravitational acceleration, the fact that it was pushed outward from the Sun faster than any known force could explain, was physically consistent with the behaviour of a light sail, an extremely thin reflective structure that uses radiation pressure from stars as propulsion. The claim was and remains controversial. Many astronomers favour natural explanations involving unusual outgassing of hydrogen or other volatiles. The debate has not been resolved because the data available on Oumuamua was insufficient to definitively distinguish between competing models, but the papers establish something that has proven durable regardless of how the Oumuamua question is ultimately settled. Interstellar objects are legitimate candidates for technosignature analysis. They are not signals we are waiting to receive from distant stars. They are physical objects that arrive in our solar system and can be studied directly, with the full range of instruments available to modern observational astronomy. 3I Atlas is, by any measure, the most extensively observed interstellar object in the history of the field. The instruments pointed at it are more numerous and more sensitive than anything available during Oumuamua's passage. The observational campaign has been organised in advance rather than improvised after the fact. The encounter geometry is known, the anomalies are documented, and the scientific framework for interpreting those anomalies as potential technosignatures, developed painfully and controversially in the years since Oumuamua, is now mature enough to be applied systematically rather than speculatively. Whether 3I Atlas proves to be natural or artificial, the encounter is going to generate data that advances the technosignature field in fundamental ways. If it behaves like a comet, we will have the most detailed characterization of an interstellar comet ever obtained, and our models of natural interstellar object behavior will improve dramatically. If it behaves like something else, if the encounter with Jupiter's magnetosphere produces signatures that cannot be explained by natural physics, we will have something considerably more important than an improved comet model. We will have the first confirmed detection of technology that did not originate here. Either result advances science, one of them advances everything else as well, and we are 11 days from knowing which one it is. Part 15. The Test. On March 16th. Every theory, no matter how elegant, no matter how internally consistent, no matter how well it explains every piece of available data, is worth precisely nothing until it makes a prediction that can be tested. This is the contract at the centre of science, not that theories must be proven beyond all doubt, but that they must be falsifiable. They must commit to telling you what they predict will happen, under what conditions, and with what measurable signature. And then they must be willing to be wrong. A theory that can accommodate any possible outcome, that bends and flexes to explain whatever the data shows regardless of what the data shows, is not a scientific theory. It is a story. The emerging theory about 3I Atlas is not a story. It is a hypothesis with specific, testable, time-stamped predictions. And the timestamp reads March 16th, 2026. The predictions are not vague. They are not the kind of soft, hedged forecasts that can be declared successful after the fact by generous interpretation. They are precise enough to distinguish clearly between confirmation and refutation, which is exactly what a good scientific prediction should be. If 3I Atlas is an engineered object approaching Jupiter's magnetosphere with the intent to interact with the Io flux tube system and use Jupiter's natural radio output as a transmission amplifier, then specific, measurable things should happen during the encounter window. Things that would not happen if the object is simply a comet passing through a magnetic field on its way out of the solar system. The first and most directly testable prediction concerns Jupiter's decometric radio emissions. Jupiter's natural radio output in the 10 to 40 MHz range is one of the best characterized phenomena in planetary astronomy. Decades of ground-based monitoring have produced a detailed statistical picture of what those emissions look like under normal conditions, their typical intensity, their burst duration, their frequency distribution, and crucially, how all of those parameters vary with the position of Io in its orbit and the rotational phase of Jupiter itself. This baseline is precise enough that a statistically significant departure from it would be identifiable within hours of the encounter. Radio telescope arrays around the world are allocated and ready. The monitoring is continuous. If 3I Atlas injects energy into the magnetospheric system in a controlled, patterned way during its passage, Jupiter's radio output should carry that pattern, not as subtle background noise requiring months of statistical analysis to extract, but as a measurable deviation that stands out against the baseline the way a voice stands out against the hum of a quiet room. Either the radio emissions behave normally on March 16th, or they do not. That answer will come quickly. The second prediction involves the Io flux tube aurora, the permanent bright spot on Jupiter's polar regions where the electrical current flowing from Io connects to the planet's atmosphere and deposits energy as ultraviolet light. This aurora is observable from Earth with space-based ultraviolet telescopes and has been monitored extensively, providing another well-characterized baseline against which anomalies can be measured. An injection of additional energy into the flux tube system, whether from a natural magnetospheric interaction or from something more deliberate, should alter the brightness and spatial morphology of that aurora in a detectable way. The Hubble Space Telescope has the ultraviolet sensitivity to see this. Observation time has been allocated. If the flux tube aurora brightens, expands, or changes its pattern in a way correlated with the position and timing of the 3I Atlas encounter, that correlation will be in the data. If it shows nothing unusual, that will also be in the data. The aurora does not lie. The third prediction concerns the object itself. 3I Atlas has been tracked with sufficient astrometric precision to establish a well-constrained baseline trajectory. The forces acting on a natural comet at this distance from the Sun, gravitational attraction, solar radiation pressure, and outgassing thrust from sublimating ices, are understood well enough to predict where the object should be at any given moment with considerable accuracy. If the object is actively maneuvering, if its trajectory adjusts in a controlled way during or after the magnetospheric encounter in a manner that cannot be attributed to those known forces, that deviation will show up in the astrometry. The network tracking 3I Atlas has been accumulating precise positional measurements for months. The baseline is solid. Any departure from the predicted path that exceeds the expected range of non-gravitational force effects would be a significant and unambiguous data point. Comets do not make controlled course corrections. If something changes in the trajectory after March 16th in a way that looks deliberate rather than incidental, the astrometry will show it. The fourth prediction is perhaps the most visually compelling. Those three perfectly symmetric jets, the ones that have been firing steadily in conditions where they should have gone quiet weeks ago, should show changes around the time of the magnetospheric encounter if they are functionally related to the approach rather than naturally driven. If the jets are a propulsion or stabilization system, their behavior during and after the encounter should differ from their behavior during the approach. A sudden increase in activity as the object enters the magnetosphere. A cessation of activity after the encounter is complete. A change in the brightness ratio between the jets suggesting differential throttling. Any of these would be detectable in the ongoing photometric monitoring of 3I Atlas. Natural comet jets do not change their behavior in response to entering a planetary magnetosphere. There is no physical mechanism by which a sublimation-driven jet would know it had crossed a magnetospheric boundary and respond to that crossing. If the jets change at the boundary, the change is telling us something. The less dramatic outcomes deserve equal and honest attention, because science does not get to choose its results, and intellectual honesty requires naming all possibilities with the same clarity. It is entirely possible that nothing unusual happens on March 16th. 3I Atlas crosses Jupiter's outer magnetosphere, produces no anomalous radio effects, generates no detectable flux tube disturbance, continues on its outbound trajectory without measurable deviation, and slowly fades beyond the range of available instruments as it moves into the outer solar system and eventually back into interstellar space. If that happens, the natural comet interpretation gains substantial support. The 6 anomalies remain. They do not disappear simply because the encounter produced nothing anomalous, but the absence of any interaction signature during the Jupiter passage would significantly undercut the hypothesis that they are all components of a single coherent engineered event. It would suggest that the jet geometry is a geological coincidence, the trajectory alignment is a numerical coincidence, the juice saturation was an instrument anomaly, and the emission frequency was a naturally occurring hydroxyl detection. Each anomaly reverts to its individual natural explanation, and the stack dissolves. Most astronomers would sleep more soundly. A few would keep looking. But consider the other possibility with the same clarity and the same willingness to follow the logic wherever it leads. Consider the outcome in which Jupiter's radio emissions deviate from their decades-long baseline on March 16th, in a structured, non-random, statistically unambiguous way, in which the Io flux tube aurora brightens at a time and in a pattern that correlates precisely with the object's magnetospheric position, in which spectrometers monitoring the encounter detect a sustained, directed narrowband emission at 1665 MHz, the hydroxyl frequency, the waterhole boundary, the frequency that 50 years of SETI reasoning has identified as the universal signal of a civilization that understands chemistry, in which the trajectory of 3I Atlas shows a controlled, purposeful adjustment after the magnetospheric passage that no natural force can explain, in which, in other words, all 6 anomalies reveal themselves to have been not a collection of independent coincidences, but the components of a single, coherent, pre-planned event, a transmission, executed by an object that has been travelling across interstellar space for longer than human civilization has existed, arriving at the one location in this solar system where the available electromagnetic infrastructure could make it loud enough to be heard across the galaxy. What would that mean? Not in the abstract philosophical sense, but concretely, for the species that has been asking this particular question since before recorded history. It would mean that we are not alone, not as a statistical inference or a Drake equation estimate, but as a confirmed observational fact. It would mean that someone already knows about us, that the 100 years of electromagnetic signals we have been broadcasting into the galaxy without fully appreciating what we were doing have been received and acted upon. It would mean that the universe is not the empty, indifferent, silent expanse that the absence of confirmed contact has sometimes made it feel like. It would mean that March 16th, 2026, a Monday, an otherwise entirely unremarkable Monday, is the day the longest question in human history receives its first concrete answer. It would mean we are at the beginning of something, not the end of anything, but the beginning of a different kind of story entirely. And it would mean that the loneliness which has quietly coloured the human relationship with the cosmos since we first looked up at the night sky and felt how small we were, that loneliness was never the truth of our situation. It was simply the limit of our instruments. The test is 11 days away. The instruments are ready. The spacecraft are in position. The radio arrays are allocated. The theory is on the table, fully committed, making predictions it cannot take back. Science will do what science has always done. Gather the data, follow the evidence without flinching, and update its understanding of the universe regardless of how uncomfortable that update turns out to be. Whether the answer is a quiet comet passing unremarkably through a magnetic field, or something that rewrites the opening paragraph of every book about humanity's place in the cosmos, we will have data. Real data. Unambiguous data. An answer that does not require interpretation or inference or the generous reading of incomplete observations. Whatever happens near Jupiter on March 16th, we will know what happened. And whatever that turns out to be, the fact that we looked carefully enough at a small, fast-moving object crossing the outer solar system and noticed that 6 things about it did not add up, and then followed that thread with rigour and honesty all the way to its conclusion, that is science working exactly as it is supposed to work. We looked up. We noticed something strange. We did not look away. Whatever is out there, that has always been the right response. And on March 16th, for the first time in the history of this particular question, we will find out whether something out there noticed us doing it.